My name is Nishcha Rathi and this is my lab report for Physics 2 Lab 3. In this lab, we will be measuring the distance dependence of the magnetic field due to a small bar magnet, and then compare our measurements to the distance dependence predicted by the equations for the on and off axis magnetic fields derived from the Biot-Savart law. In this lab, the system we are going to be analyzing is the bar magnet and the surroundings are the Earth. In this experiment, using the equation that the magnetic field is equal to kr to the power n, the brief results that we have found is that n is equal to minus 5.99, the k is equal to 4.3053 times 10 to the minus 10, the magnetic field off axis is equal to 4.7 times 10 to the minus 5 teslas, and the magnetic moment is 0.00215 joules per tesla. We are going to be using the following physical principles. Biot-Savart's law, which gives us an equation for the magnetic field, and the distance dependence relationship, which says that the magnetic field due to a bar magnet is equal to k r to the power n. When converted into a logarithmic form, this is that the ln of bx is equal to ln k plus n ln r. The procedure for this experiment, the first thing we do is to find the magnetometer sensor within the phone. Then we are going to take different distances and measure the y component of the magnetic field generated by the magnet. In other words, we are going to find the d perpendiculars shown in the diagram below at each of the following magnetic fields equal to 20, 70, 120, 170 and 220 microteslas. This helps us estimate magnetic field for each of the distance r and then generate a graph. The procedure for the experiment is that we measure the final d perpendicular for b equal to 100 microteslas, then take a magnetometer up a distance d perpendicular, and then measure the magnetic field here accounting for the Earth's field. This is the 45 degrees off-axis magnetic force due to a bar magnet. We observed that the position of the magnetometer has no effect on the measured x component of the magnetic field. The measured values in the lab have been shown below. The replicates for each of the magnetic fields and the measured distances has been given, and the average of the magnetic field with the average of the distance was computed and graphed. The off-axis field was also measured, and then this is the data we generated using that. Finally, after processing the data, we got the measured values out, that n is equal to minus 5.99, the k is equal to 4.3053 times 10 to the minus 10, the magnetic field off axis was 4.7 times 10 to the minus 5 teslas, and the magnetic moment due to the dipole was 0.00215 joules per tesla. This was what we had seen in our preview for the lab results. Finally, we then created a computational model using the Biot-Savart's law, which we have seen before in GlowScript. The computational model accounted for the various distances and also created a comparative graph. The modeled values, we found that b is equal to 2, in this image shown here, the b is equal to 2.281 times 10 to the minus 8 teslas. We found that the two measured values vastly differed from the computed values. The n, which should have been minus 3, but we measured it to be minus 6, and the magnetic field off axis was measured to be 4.7 times 10 to the minus 5, whereas we expected the computed value to be around 2.3 times 10 to the power minus 8 teslas. These values could be different because of the various sources of errors. Number one, there was quite a bit of inaccuracy in the magnetometer app, which could have led to this error. There is also a human error, including slight shifts in the ruler, causing change in the net field, which is being caused due to the Earth. Finally, what if we hadn't oriented our experiment to compensate for the magnetic north and had instead laid out our meter stick at some intermediate angle with respect to the Earth's magnetic field? This would change our results because laying the bar magnet along the east-west axis makes the magnetic field perpendicular to its length, ensuring in our x-axis we don't include the Earth's magnetic field. If we didn't do this, this field across the x-axis would be greater than 0 teslas. And what if we were to stick two identical magnets together end to end and run the experiment again? The magnetic dipole would increase, hence increasing the field strength, and this would mean that our measured D values would be larger since the field would the required value only at a greater distance away. So that was the lab report for lab 3. Thank you so much.